Hi and welcome back to another automation video with the Siemens S7-1200 and Factory I/O. In this video we add the integration part of the PID controller to the proportional part we implemented in the previous video. We also show how to calculate the total error by estimating the area under the curve, which is key to understanding how the integral part of a PID controller operates. So let's get started. Welcome back. Now this is where we were at the end of the last video where we took a look at proportional control. Now before we start, I would just like to make a little more room on the Factory I/O screen by removing any tags from the dock that we don't need to monitor. Okay, we don't need to monitor drain, the reset light, the start and stop lights, or the stop button. Okay, that is enough. Now there is one thing we should have clamped in the last video that we will do now before we start programming the integral part of the PID controller. However, it's easier to explain when we see it in action. So let's run the proportional controller again and see what happens. Let's check the status of the tags in the watch table. Okay, everything is zeroed and ready to go. Let's put Factory I/O into play mode, and in the watch table accept the gain of 20 and the set point 6.65, which translates to 200 centimeters. Okay, the tank starts to fill and we can see fill valve temp is larger than 10. So the value sent to the fill valve is clamped to 10 with the code here. However, soon as the fill valve temp value gets below 10, this value is then written to the fill valve. Then as soon as the set point is reached, the fill valve closes to prevent any further water entering the tank. But we overshoot the set point slightly and therefore we get a slight negative error. This error is multiplied by the gain and gives us a value of approximately minus 2.2, which is written to the fill valve. And here's the problem. The fill valve operates between 0 and 10 volts. So we need to clamp for 0 as well as 10. In fact, there are a couple of changes we need to make to this clamping code, so let's do them now. Let's stop Factory I/O and the PLC. Let's go offline too. So we need to check for when the output is greater than 10 and less than 0. So let's remove the equals from the first line and then add a second line to check for less than 0. So I'll just make some space and copy the else if statement, paste it in the space we just made, then modify it. So paste, then change less than 10 to less than 0. Then change fill valve temp to equal 0. Now in the last else if we need to check for when the fill valve temp output is between 10 and 0, and if it is, write the value directly to the fill valve. So if fill valve temp is less or equal to 10 and fill valve temp is greater or equal to 0, then fill valve is equal to fill valve temp. Great, let's upload the code to the PLC and see what happens. Now let's run the PLC and monitor the variables in the watch table. not forgetting to put factory I/O into play mode. Now we are ready to apply the set point and the proportional gain to the controller via the watch table. So the tank starts to fill, and we can see that fill valve temp is getting bigger. So we then write 10 to the fill valve. Now let's see what happens to the fill valve when the set point is reached and we overshoot the set point and get a slight negative error. As we can see, fill valve temp is now a negative value, so we write 0 to the fill valve. Great, that works fine. Okay, now that we have clamped the output sent to the fill valve between 10 and 0 volts, we can start looking at what is required for the integral part of the controller. So let's take a look at the PID controller in its discrete form, and if you can remember, in the previous video we programmed the proportional part highlighted here. So in this video we will be adding the code for the integral part of the PID controller shown here, where instead of just using the error at a particular time, we use the total error. This includes the sum of all the previous errors as well as the current error. And then we multiply it by the time constant t, which, if you can remember from the previous video, was the time set for the interrupt. So the code we need to add will look like this: gain times total error times t. Now let's go back to the animated diagram we used in the proportional control video to show how the error is calculated. The error is the difference between the water level and the set point, as shown here. Now the reason I showed it this way was to help explain how the error was calculated. However, we really should have plotted a separate graph of the error reducing as the water level increases. So let's remove the existing plot and replace the text saying level with error and add in the value of 200 for the set point and 0 for the base. Now let's start filling the tank again while keeping everything else the same on the graph. This might seem a bit confusing at present, but bear with me and hopefully it will become a little clearer. So here we go. So we see the yellow error line being plotted, which is the inverse of the blue level line. So as the error comes down, the level goes up. Okay, now let's move the yellow arrows below the newly plotted error line. As we can see, they fit perfectly under the line. Now, if you studied pure maths at school or university, you may remember that we integrate by calculating the area below the curve or plotted line on the graph. So how do we calculate this area? Well, we do this by multiplying the error line by the time interval t, basically the height by the width, and then adding them all together. Obviously this is an approximation, as can be seen in the diagram. However, if we make the time interval smaller, then the area under the curve would be closer to the actual value, as shown here. In fact, the smaller the sample time, the more accurate the calculation. Although for this tank system, we really don't need the sample time to be too small. Now, sometimes it's difficult to visualize what is happening here, so I'll come back to this in just a moment when we've entered some code, as I think it will be easier to follow. Now, before we start coding, let's add some tags, modify the watch table to include some of these tags, then start modifying the fill valve code. Okay, let's open up the tag table, and at the bottom let's add some tags. We'll add sum of previous errors, which, as the name suggests, this is a running total of all the previous errors. Then we'll add t for the time constant, which is the value we set up for the interrupt, so that the error can be calculated accurately every t seconds when the PLC scans the fill valve code. The next tag is total error, which is the sum of the previous errors plus the present error. And then the last tag is the integral gain Ki. Great, now let's add some of these tags to the watch table. I'm just going to insert total error next to scaled error. And then I'll insert Ki next to Kp. Oops, I'll move it up in a moment. Okay, that's done. Now I'll just enter t for the integral time constant. Great, now we can start modifying the code for the valve control function to include integration. So I'm going to amend the code on line 11 to include the integral, but first let's add brackets around the proportional part of the code. Then we include add and open new brackets and type in Ki times the total error times t, and then close the brackets. However, we have to calculate the total error before this line, so let's insert some space, then enter total error is equal to the scaled error plus sum of previous errors. The scaled error being the error between 0 and 300, but scaled to between 0 and 10. So on the first scan of the PLC interrupt valve control function, the total error will only be the scaled error, as the previous error is 0 at this stage. Then at the bottom of the valve control function, we need to update the sum of the previous errors so that it may be used on the next scan of the valve control function. And the way we do that is by entering sum of previous errors is equal to the total error after the clamping code. So on the next scan of the valve control function code, the total error will be equal to the previous total error, now called the sum of previous errors, plus the new scaled error. Right, let's upload the updated code to the PLC, ready for us to run the program. Now that we've entered the code, it should help us to understand how the accumulation of errors multiplied by t represents the area under the curve. So let's have a look at the graph we looked at earlier one more time. Okay, this is the graph we plotted of the error reducing in time calculated at set intervals. So let's remove the curve or line, however you would like to refer to it, and show visually how we add up the total errors after 5 sample periods of t. If we move the yellow error lines and place them on top of each other to illustrate adding them up, we then get the total error so far. Then if we multiply the total error, as in the equation, by t, we effectively get an approximation of the area under the curve, the integral, which can then be multiplied by the gain Ki. Not forgetting that the total error is equal to the sum of the previous errors plus the present error. So the first 4 arrows could be considered the sum of previous errors plus the small error which is calculated on the next scan. Okay, hope that makes things a little clearer on how we integrate to calculate the area under the curve. Now, what about the gains Kp and Ki? How do we calculate those? Well, in the previous proportional control video, we mentioned the Ziegler-Nichols method and how a good starting point for Kp was 0.5 times Ku, Ku being the critical gain at which oscillations occur, which was 41. Check out the first PID video to see how we arrived at this at 7 minutes 23 seconds. Now, when we go to the PI controller, the Ziegler-Nichols method recommends Kp between 0.45 times Ku and Ki is 0.54 times Ku divided by Tu, Tu being the period between oscillations, which was approximately 6.3. You can see this in the first PID video gain at 7 minutes 45 seconds. So Kp works out to be approximately 18 and Ki approximately 3.5 as a starting point. However, instead of using 3.5, I'm going to work my way up from 0.3. Now, from the previous video, you may also remember how we worked out the interrupt time constant. And you can see this in the previous video at timing 23 minutes and 10 seconds to see how we did it. But what I can say is it was based on the time it took the tank to fill from empty to 63% of the required 200 centimeters, which worked out to be 17.64 seconds. I then mentioned we needed a figure of at least 10 times faster than this, but that I decided on approximately 100 times faster after some investigation, which is approximately 200 milliseconds. So to shed some light on this, I'm going to test what happens when we use different interrupt time constants so we can see how the controller reacts. We'll use 100 milliseconds, 200 milliseconds, 600 milliseconds, 1 second, and maybe even 1.7 seconds. Now let's run the PLC to zero the variables. Let's put factory I/O into play mode. Then we can input Ki to 0.3 as an initial value and modify Kp to 18. Then change T to 100 milliseconds. Now I just need to upload the code to the PLC and then we will be ready to go. But I will leave the upload and the running of the program to the next video, as I've gone on for quite a lot of time. However, I'll just mention that there is a little more code to add to ensure the controller works well with the water tank. So do watch the next video to find out how it all works. So hope you found this video informative. Thanks for watching. If you've enjoyed the video, please give it the thumbs up. And if you'd like to learn more, then please click the subscribe button and the bell so you'll be informed as soon as a new video is uploaded. Please see the links in the description should you wish to get a free 30-day license for Factory I/O, and also check out my Patreon account. and I'll see you in the next video. Bye for now.